Okay, I guess we can start now. I think many people already joined, so no need to wait any longer. So welcome everyone to the MMSys 20 Technical Program Demo and Industry Track Session 1. My name is Emre Aksu. I'm from Nokia Technologies and I'll be the chair of this session. So just some brief information. I hope all of you can see the presentation. Yeah, we're going online. Hopefully next year in Istanbul, we will be face-to-face. Then Demo and Industry Track, there will be 2 sessions. One of them is today, June 9, right now, and the other one is tomorrow, same time. In virtual room 2, you all have the link for that. Then just some practical information about session 1. This is related to immersive media and its applications. And for questions, please use Slido. I think it's a good system. And there's a room for in Slido for entering your questions. And for the questions, please use the label as the paper ID, the paper number. The list of the filter items are there. That will make life easier for us later on during the Q&A session. In Zoom, everybody will be muted, as you now see. Please raise hands if needed, and if you want to say something or for some reason, if you need to raise your hand, that's the only way you can notify me. Then I may ask you to unmute. Please pay attention to the screen during that time, and I will be setting you co-host for the presenters, especially when you need to present your content and your paper. So we will have around 5 minutes per person, per presenter, to present the demo slides and the material. Please be brief and concise and leave the questions in the Slido, to the Slido and Slack, and we will mostly go through the questions during that time. We will have enough time, I hope, for the questions. But with the questions round, we will take 1 question at a time per paper and go in rounds to be fair to everybody who has their paper. All right, so these are the number of papers. So we have 7 papers to go through and present. The names in bold are the presenters. Hopefully we had a test session before this session with them and things worked out fine. So hopefully there will be no technical glitches. And I think we can start with the first one. It's immersive media experience with MPEG OMAP, multi-viewpoints and overlays. And I'm going to now leave the floor to Kashyap to share his content and his presentation. So Kashyap Kamachi Sridhar from Nokia Technologies will be presenting. Kashyap, can you hear me?
Yeah, hi Emre.
Hi.
Can you hear me?
Yes, now you're also co-host, so you can present. I will stop sharing.
Okay, thank you very much. And hello everyone. So I'll be sharing my screen. I hope you are able to see my screen.
Yes.
Yeah, so basically in this paper, we are presenting immersive media experiences with MPEG OMAP, mainly the features on multi-viewpoint and overlays. So we know that immersive media experiences such as virtual reality make use of 360-degree videos to provide the sense of immersion. And in order to avoid multiple solutions on this and to ease the deployment, the Moving Pictures Expert Group, or MPEG, created the omnidirectional media format, also known as the OMAF standard. So the OMAF standard defines the storage and delivery formats for omnidirectional media, and the media may include videos, images, audio, and text. So among many things, the first edition of OMAF defined video profile, namely the HEVC-based viewport-dependent media profile. So this profile enables the delivery of 360-degree videos, such that the viewport, the videos in the viewport can be delivered at high fidelity as compared to the other parts of the 360-degree video. So a viewport may be defined as a small portion of the whole 360-degree video. So as you can see, the viewport dependent profile enables this mixed way of delivering 360-degree videos, which can make use of, for example, the tiles as used in HEVC-based video coding. So the second edition of OMAF, among again many features, defines two major features, which is the overlays and the multiple viewpoints. Overlays have been researched over the years and have been seen that it enhances the immersive experience of this 360-degree video. So for example, so this is, for example, the background 360-degree video, and this could be one of an overlay. So overlays can be of multiple types. One is a spherical overlay, a 2D overlay, and an overlay which, for example, here you can see in the red, which is always in the viewport of the user. So a user is assumed to be in the center of the 360-degree video, and the green lines here suggest the viewport, the current viewport of the user. So as the user rotates his head, the overlay, which is always in his viewport, also rotates along with his rotation. So as with respect to multiple viewpoints, an example of a viewpoint can be a 360-degree video captured from a omnidirectional camera. So multiple viewpoints, for example, maybe like two 360-degree cameras capturing a football game, for example. And here is again an example of a multiple viewpoint framework, where a user may start with one of the viewpoints, look around, and then each viewpoint may have its own overlays, and then the user may switch to a new viewpoint and again look around, and then he'll be able to switch to a third viewpoint, for example.
Kashyap, you have 1 minute left.
Yeah. Okay. So this is the system architecture, which again uses HEVC-based encoding and the ISO-based media file format and the dash. So, okay, maybe I will move to the demo. So here, okay, this is one of the viewpoint, and you can see a overlay pop up, which shows where the user can switch to a new viewpoint. Yeah. So maybe I can just forward a bit. Yeah, this is one of second viewpoint which the user can switch to. So here you can see a 2D overlay, and there is a Nokia logo here, which is always in the viewport of the user. And there are other overlays in this viewpoint. For example, you can see some text overlays here. And a user can also make some user interaction with the overlay. For example, I can enable one of the overlays, which is here, and it will pop up a overlay canvas and starts playing back a new overlay.
Last words, please.
Yeah.
Kashyap.
Okay. Yeah. So as a next step, we are looking into improving the viewpoint switching algorithm, and also optimizing the viewport dependent streaming. Yeah. Thank you.
Thanks, Kashyap.
Yeah.
Please post your questions in Slido, and we will come back to them at the end of the session. So I'd like to know, you, Kashyap, thanks. Now let's move to the second paper, VVC bitstream extraction and merging operations for multi-stream media applications. And Karim will be presenting this paper from TNO. Let's see. Karim is not here. I'm not sure if he's dropped from the call because I saw him before. So, oh, okay, Alexander will present. All right, sorry, I will now change that.
Hi.
Hi, Alexander. Okay, please go on with the presentation.
Yes. Hi, so can you see my screen now? The PowerPoint presentation?
Yes, it is visible.
Yes, okay. So hello everyone, my name is Alexander Gabriel, and I'll be presenting the demo paper VVC bitstream extraction and merging operations for multi-stream media applications. So I'll start off by talking about the use cases that we're thinking about in this demo. The first one is video conferencing, where one user may be receiving multiple streams. Another case is 360 video, where a user might be receiving multiple segments of the same stream and might want to assemble them and decode them in one decoder. And another use case is where you might want to extract a certain part of a video and don't want to receive all of the other parts of the video. So the architecture with which we've worked with to demonstrate our demo is basically we encode the content and then we merge the content into one bitstream and then we decode the content. And the innovative step or the real interesting part here is where we merge the content into one bitstream in the coded domain. And this saves a lot of time because you don't need to decode or parse too many of the elements of the video stream. So what we've done is we've taken two videos and we've encoded with the VVC encoder from JVET and MPEG, and we get two bit streams. We then use a stream merger, which will basically put these two streams together in the coded domain. So it will read the null units and place them into an output VVC file. And then we run it through a modified decoder and we get an output video. So we only have one decoder that decodes two of these bit streams. So with that said, I'll show a quick demo. So what we have here in the bottom right corner is FF1, which is the left part of a sequence, and this is just the YUV. What we have in 2 is the right part. So you'll see here, it's just the right part of the sequence. And what I'm going to do now is I'm going to merge these sequences using the stream merge app that you can see here. So I'm going to put FF1, FF2, and FF1. And the output will be FFFF.vvc. This configuration that you see here, jigsaw with the numbers following it, is a syntax that we've created so that we know how these videos relate to each other. If you're curious about it, you can look into the paper or watch the video that we've provided. So what I'm doing here now is merging around 50 frames, and you'll see that it took around 0.34 seconds, so it is real time since the sequence was 50 FPS. And now what I'm going to do is play that or decode that content. So this is the command that I have where I have the decoder app. I input the bitstream file and I'm piping that out into just standard output. This is something that we had to add. It's then pipes into FFplay, which basically plays it as a raw format. And here on the right, these commands are just for positioning the video. If I click enter, you can see that one decoder application is actually decoding these 3-bit streams, or what was originally 3-bit streams. So I think that's pretty much all we wanted to say. Well, we'll be happy to answer any questions.
Thank you, Alexander. I guess we'll take the questions in the Slido. So this was paper 2. So while posting your questions in Slido, please make sure that you label it correctly. Thanks a lot for the presentation.
Thanks.
Okay, so now let's move on to the third demo paper, which is a pipeline for multi-party volumetric video conferencing, transmission of point clouds over low latency dash. And Jack Jensen from CWI will be presenting this paper. Let me enable. Just a second. Jack, can you hear me?
Yeah, I can hear you. And I hope
yes, yes, we can hear you. And now you're co-host, so you can share your screen as well.
I'll just say nothing and just share the video.
Okay.
I can find it. That one. Yeah.
Good morning. My name is Jack Jansen from CWI in Amsterdam, and I am here to present our contribution, a pipeline for multi-party volumetric video conferencing, transmission of point clouds over low latency dash. The contribution is centered around video conferencing, and specifically volumetric video conferencing, where you do not transmit flat video, but you transmit volumetric video. The main contributions of our paper are the fact that we use point clouds for the volumetric data, and the fact that we use low latency dash for the transmission of that point cloud data. But let me first show you our demonstration setup, the one that we were going to bring to Istanbul, but unfortunately that was not possible. I'm standing here in our 3D studio, where you can see the 4 capture cameras that will capture the local user, and you can see the head-mounted display that the user will use to see the actual scene and the self-view and the view of the other people. If we move on, then you can see here the workstation class PC that is used to capture the video and to render the scene, which is currently empty. If we move on, you see here our second setup, which consists of a fairly capable laptop and a single camera and no head-mounted display. In this setup, the 2 systems are placed next to each other, but actually the data is transmitted off-site, actually to Paris, France. So the point clouds from here are sent to France and sent back to this computer to be displayed, and those point clouds are sent to France and back to be displayed. And the same for the conversational audio. Let us now have a look on the system in operation. Here, that's a nice blouse. Where did you get it?
Thanks. Thanks to share. I got it at Hey Mom. Hey, those are some really cool shoes. Where'd you get them?
Oh, they're really old. I bought them about 5 years ago. But also at Hey, that's a nice blouse. Where did you get it?
Thanks. Thanks to share. I got it at Hey Mom. Hey, those are some really cool shoes. Where'd you get them?
Oh, they're really old. I bought them about 5 years ago. But also at Hey Mom. Hey, Alina, that's a nice blouse. Where did you get it?
Thanks. Thanks to share. I got it at Hey Mom. Hey, those are some really cool shoes. Where'd you get them?
Oh, they're really old. I got them about 5 years ago. But also at Hey Mom.
And I guess that is about the best I can do to share volumetric video conferencing demos over flat video.
Thanks, Jack, for the nice demonstration as well. We'll take the questions in the Slido session. So the paper ID was paper 3. So if you're going to post questions, please add that label. And I will now mute you. Let's move on. Oops, sorry. So the 4th paper is cloud rendering-based volumetric video streaming system for mixed reality services. And Dmitry Podborsky from Fraunhofer HHI is going to present the paper. Dmitry, can you unmute?
Yes, can you hear me?
Yes, we can hear you very well. So I'm making you co-host now. Now you can share your material. Please go ahead.
So let me share my screen. It's actually my first time using Zoom.
Yes, you also missed the test session. I know. Let's hope there will be no hiccups. But let me know if you need any.
Okay, can you see it now?
Yes, we can see your screen.
Okay, so we're gonna talk about volumetric video and cloud rendering of it. So what we have here, let me maybe get rid of this. So what we have here in our case, we have textures, we have meshes, so we render them together in the volumetric video. And we package this volumetric video into an MP4 file in separate tracks. So we have textures encoded with H.264 or whatever encoder you like as a video bitstream. And then we have meshes, which we also encode in order to compress the data in a separate track. And then we put them in the same MP4 file. But however, this is some problematic. So we have some problems playing back this volumetric content on Android, like on smartphones and on devices which does not have so much power. So what we are proposing and what we describe in our paper is a cloud-based concept where we basically shift all the rendering, all the processing, all this heavy load processing to the server. And basically the client then just sends some control data where its viewport is located or how it's interact with some objects and so on. And it also has ability to control the playback. Everything is done then on the server side, and then it's sent back as a 2D video back to the client. So the client is then really simple. It just has to be able to decode a 2D video, which is nowadays really simple to do on almost any device. And also an advantage of it is that you can really write a browser applications, for example, for such scenarios, and you can basically deploy your application on many, many different devices. And this is basically like a short video showing this in action. Like you have a 2D client on the left side, like moving around using WASD buttons on the keyboard and some sliders. And on the right side, you see like the server side. In this case, it's running in the Unity editor. So you basically can see how the object is moving around when client sends this control data to server. So it's like a cloud gaming kind of concept for volumetric video playback. And one of the most important metrics for such a system is obviously the delay, since we are doing processing now and on the server. So we need to be really fast so that the quality of experience is in a good shape, I would say. So the motion to photon latency is really important in this scenario. And for that, we utilize many different tools which are available. So for example, for encoding, we use obviously hardware, in this case, NVIDIA encoding. API is quite handy. Then we use WebRTC for ultra low latency streaming. So we have some projects with telecom as well. So we do some experiments on using 5G networks as well. And we have also to do viewport prediction, which also we have another paper where Serhan gonna explain it, I guess on Thursday, when I remember correctly. So we have to do some prediction as well, so to compensate this latency. And then we can also do some post-rendering correction on the client side as well. And for the latency measurement, we also developed some application, so several applications to measure this motion to photon latency. So in this case, we measure it using the web browser application where the client is first establishing the connection to server. It's then basically starting the video stream, and then we are requesting the texture color to change, start our measurement, and then we are waiting on the client side until this color is really detected. Until that, we then measure the motion to photon latency. And I also have some additional information which I can share on probably more details to this. So yeah, thank you. I would be really hoping to answer some nice questions regarding this, and hope it's interesting to some of you. Thank you.
Thanks, Dimitri, for the nice presentation and also being on time. And for the Slido, the paper ID is paper 4 for this paper. So while posting, please note that as labeled in your questions. So now I'll move on to 5. Multimodal video forensic platform for investigating post-terrorist attack scenarios. I assume Alexander will be presenting that. So who will be the presenter of this paper? Can you share in the chat? Okay, perhaps we have a no-show here, so I'll move on then to presentation 6. So fixed viewpoint applications for omnidirectional video content, combining traditional and 360 video for immersive experiences. And I guess Emmanuel is going to present this from TNO, so I'll just a second. Emmanuel, can you hear me?
Yes, I can hear you.
Great. So now I'll give you the co-host. I'm making you the co-host now, so please go on. Yeah.
Okay. Hello. I am Emmanuel from TNO, and I'm going to present you the fixed viewport applications for directional video content with the subtitle Combining Traditional and 360 Video for Immersive Experiences. Typically in 360 video, we have the user controlling the viewport. Thus, it enhances the feeling of immersion and allows for an explorative experience. While in traditional video, we have what? Oh, sorry. You couldn't see my screen before. Can you see it now?
Yes, we can see now. Yeah.
Okay. So, while in traditional video, we have has been around for decades. Again, it doesn't work now. So, and we have like directive techniques that has been developed in a long time. So we have a trade-off between having immersion in omnidirectional video and having expressiveness that we have in traditional video. So in omnidirectional video, for example, here we can watch wherever we want, and but we might miss the action that in this case might be taking place inside the yellow square, which looks boring, while we have a red bright object right in front of us, so the user might be looking over there. And as we can see in the interesting part, there are some people around. So the current approach is to try to direct the attention of the user, which typically happens with visual marks or altering the video content, or forcing a change in the viewport. But there are several disadvantages in each approach, either sickness or limiting the content creator's creativity. So what we are proposing is having an omnidirectional video in the 360 mode whenever the immersion is paramount and we have an exploratory scenario, while when we want to switch traditional video, what we call director modes, it's when we have a specific point of action that the user would like to follow. And in order to do this seamlessly, we propose doing it in a virtual environment. So we are fixing the viewport in the director's mode, but the user is able to look around in the virtual environment, thus doesn't lose the immersion part. I will not go into the details of the implementation, but roughly speaking, the circle is what we have in the immersive mode, while the square is the virtual environment that unfolds in the director's mode, and the yellow dotted part, it's the content that remains visible during the director's mode. This is an example scene in the 360 mode, and this is the same scene as it would look in the director's mode in a fake virtual cinema. We have a video recording of the platform in action. It's the same scene as you saw before. The user can navigate freely in the 360 mode. As you can see, there is a chair indicating the central position of the user, just so they will not be lost in the scene. And as you can see, at this point, we are switching into the director's mode. So the scene gradually fades in order not to alienate the user. And at this point, the viewport is fixed. So as you can see, there is a panning in the camera that if we were in a normal 360 mode, it will cause sickness to the user. And we can also have other effects like zoom and move without having any of the problems that typical 360 video would have. Yet at the same time, the director can have the view wherever it wants, and the immersion still remains. And then this is the way we switch back. So I will cut it a bit short, not to go over the time. So to conclude, this is a way we propose to combine traditional and directional video, having a fixed viewport, and this happens by having a 3D scene around the viewport. And we can have the director's mode for artistic expression, while the 3D mode can be used for immersion. There are, of course, several aspects to be examined, mostly on the user experience and on the technical, because we do not know specifically compression and transmission techniques that can be used for such scenario. And that's all from us, and thank you for your time.
Thanks, Emmanuel, for the presentation. And this was so paper 6 for the Slido questions. And let's move on to paper 7, Universal Access for Object-Based Media Experiences from Juliet from BBC R&D. So just a second. Juliet, can you hear me?
Yeah, I can hear you.
Okay, now I made you co-host as
Stop
well.
sharing.
Please go ahead.
You have to stop sharing your screen, I think.
Okay, so it moved the controls.
Okay.
Yes.
All good for the screen? Yeah.
Yes, we can see it. Yeah. Please go ahead.
So, hi everyone. I'm Juliet Carter, a research engineer with BBC R&D. So recently, we've been looking at how we can deliver object-based media experiences at scale and sustainably, and how we can achieve universal access with them. So that is to deliver any experience on any device, new or legacy. So object-based media experiences are immersive experiences which defer the composition of media objects to occur on client devices based on some metadata. And that allows for a high degree of personalization, so it can fit to users' device, preference, location, viewing patterns, you name it. So obviously that has its challenges because OBM experiences can have lots of different formats. There's a growing number of devices that can play them back. They can be developed for multiple users, have multiple viewports, multiple streams, etc. So how can we write something in software that addresses these challenges? So we've identified 3 software approaches, which we think are key to deliver our object-based media experiences at scale. So we're using a single code base that works on all of our target platforms. We have an experience runtime that allows us to create a set of capabilities on top of which experiences can be built. And we use cloud rendering and remote streaming to ensure that any device can have access to any experience. So our demonstrator showcases these 3 software approaches. So it's based on the iPlayer user interface, which is a content provider service. And we can select a number of different experiences from a carousel to play back. So it is worth keeping in mind that our system works at 60 frames per second, but of course over Zoom that might not show. So the first approach is we use a single code base, which compiles and runs on all of our target platforms. So our code base is in C++. We use cross-compilation to get it working on all major browsers, Mac, Linux, Android, Raspberry Pi, and Fire TV. And we compile to WebAssembly to get it working on the browser. And obviously the benefits of using this approach is that we can easily have feature parity across all of our target platforms, and it looks the same too. And for browsers, that means that we don't have to rely on CSS. So I can quickly show you, not this or this, but this, which is the Mac. This is the demo of the Mac version, but that's the same for all of our platforms. And as you can see, I can just kind of go and choose, for example, to play back a linear AV. There is audio, but I've disabled it for this demo. So we're also using an experience runtime that provides us a toolkit of reusable capabilities on top of which these different types of experiences can be built. So these capabilities can be a render interface, video and audio playback, dash support, decoders, input systems, etc. The detailed diagram on the top is explained more thoroughly in the paper. So our runtime is based on a games engine-like runtime, which means that we can maximize GPU throughput during the scene construction of the experience. We use immediate mode rendering, we use hardware acceleration during decoding when available. We've got asset conditioning steps. And we're also using cross-platform abstraction layers, which gives us access to inputs and rendering systems. So using these capabilities, we can build a bunch of experiences. So as I demoed before, we can just play back linear AV, but we can also introduce new types of interactive experiences. So here I've got a demo of, very quick demo of a branching narrative, which work on any device. So I can navigate to this experience, which allows you to kind of make choices. So I can click on I'm ready, and that will start the experience. And the user can decide on how the story unfolds. I can choose to fight the wizard or steal his hat, for example. And finally, we want to be able to render some very complex real-time object media scenes on any device, and some client devices may not have the computational ability to do that. So we've built our remote experience streaming, or RxS system. So like any cloud-based rendering system, the rendering of the scene is offloaded to the cloud, resulting experience streamed back to the client device, user inputs captured on the client device, sent back to the server. And that means that any device can play back any experience. So that can be a laptop, tablet, or even a little Raspberry Pi Zero. And I've got this demo which shows our RxS system in real time to that experience, which uses quite a beefy NVIDIA graphics card, is on an AWS server. We've implemented touch interaction so we can navigate through the scene as well. And this is a little Raspberry Pi that costs £10, single core, 512 megabits of RAM, and we can achieve very low latency on that as well. So we can play back these experiences. So I'm actually holding up this little Raspberry Pi Zero on the camera if you want to see what it looks like. So we think it's actually quite impressive that a little Raspberry Pi can play these experiences. So that's it from me. So yeah, that our demonstrator implements these 3 software approaches to deliver universal access for object-based media experiences. That's it. Thank you.
Thanks, Juliet, for the nice presentation. And the paper ID was 7. So paper 7 for the questions in Slido, please use label paper 7 for this paper. I'm going to ask once again for paper 5, the multimodal video forensic platform for investigating post-terrorist attack scenarios. Are any of the authors here who would like to present? Please use the chat to write your presence. Otherwise, I'll move on to the questions and answers. Okay, so it seems no. Then let's move on to the Q&A session, and I will now share my screen. Can you see my screen? Okay, all right, now let me move the Slido here. So how I will do this is that this is the Slido screen, so you have been posting questions. So what I will do now is I'm going to filter out the questions starting from paper 1 and go one round so that we have enough time for everyone. We have around 15 minutes. So I guess at least one round we can go. But otherwise, please also provide your inputs here so you can reply here as well, or reach out to the question owner and then have even a Slack session. But let's start from paper 1. I'll go with the first question. So Kashyap, I'm going to unmute you. So this question is coming from Emmanuel Thomas from TNO.
Yeah.
Since the same event is recorded by different viewpoints, should I read, or I guess all of you are reading this, so probably you can just give the answer.
Yes. So
zoom in.
yes, this is a valid problem, as you know it. I think. I mean, we are yet to implement any. I mean, we are looking into a problem such as this and trying to improve the delay while switching from one viewpoint to the other. One possible solution would be to reduce the playback buffer, like for example in live streaming, so that it helps in switching to a new viewpoint with as minimal delay as possible. There could be other solutions, but yeah, we are yet to look into those things as of now.
Okay, thank you. So I also encourage any offline discussion on this topic. I'm going to mark this as, okay, I can't mark that anyway. It's the first one. So let's move on to the second paper and take the first question there. So I guess I'm going to unmute Alexander for that. Oh, you're already on mute. You can reply.
Yeah.
Yes.
So I think I showed in the demo that we do indeed only use one decoding pipeline that basically takes this merged bit stream and decodes it. And so, well, the advantage is, of course, that you don't have to have multiple decoders running, which can be quite burdensome for lower end devices. So yeah, the answer is yes, there's one decoding instance.
Okay, thank you. Right, I'll move on to paper 3. Let's take the first question. I guess this is for Jack.
Yeah, we are. We are primarily. Am I unmuted?
Yes, you are. You can hear you.
Yeah, I think we pressed the button at the same time.
Yeah.
We are really interested in conferencing applications, but we think that using point clouds as opposed to meshes has the advantage that point clouds have potentially a much lower latency because the amount of processing is less, and we will also not have issues with having to consider waterproofness of your meshes and stuff like that.
Okay.
Does that answer the question?
Thank you. Sas Karsten is here. Karsten, does the answer satisfy?
Yes.
Okay.
I was thinking of we make point clouds from LiDARs, and then the result is quite different from the RGBD cameras, right? So that's when the problem would have the same complexity, I suppose.
Yes, because with LiDARs you have much less points, much fewer points. Yeah.
Yeah. All right.
Okay, thank you. So I'll move on to paper 4. This is from Juliet, and I guess Dimitri, it's you who should answer this. You're co-host, so you can unmute yourself probably. Can you?
Yes, yes.
Yes.
You should be able to hear me now.
Yes, we can.
Yeah, delay measurements. I saw that. So actually, we are measuring with this app, which I show in the long video, the motion to photon latency entirely. So it's not only network. So what we do is we use request animation frame in the web browser, so in JavaScript, so to basically get when the browser is rendering the video on the screen, we actually looking into the value of the pixel. So we try to evaluate the color of the pixel, and when it changes, then we actually stop our timer, so to measure the latency. So, and I actually was prepared for such kind of question regarding the latency. And in this answers, which Serhan already replied 3 times to this question in Slido, you can find the YouTube video where I explain it in much more detailed way. There's a YouTube link on my YouTube channel. So then you can take a look where I actually not only showing how we measure this in browser, but I also evaluate each component, like how much of this latency coming from GStreamer framework media pipeline and how much is actually from the network. So there's some additional information.
Mm-hmm. Thank you. Thanks for actually bringing to my attention the replies. So I forgot to open that actually, so you can see the replies here already from Serhan. Yeah, right. Juliet, does that answer your question?
Yeah, I'll check out the link. Thanks for that.
Okay. Very good. So let's move on to paper 6 because paper 5 authors are not here. For paper 6, I guess it's Emmanuel. You can unmute yourself.
Yep.
All right. So please go ahead with the first question.
Concerning the loss of interactivity, this is our main argument of the paper. So what we are arguing is that we still keep the 360 mode. It's just that the difference is that instead of looking around in the video, you look around in a virtual environment. So you still have some sort of interactivity. So you don't suddenly feel like completely pinned down, especially when you're wearing a hand-mounted display. but at the same time, the creator can change only the part that you have in the fixed viewport. I think that's all I have to say.
Carsten, does that answer your question?
Yeah, I guess. I'm curious about what happens at the edges of that. I'd be interested to look at the paper more closely. I just had a scan right now. Thank you.
No problem. We also have a couple of proposed transition methods in order to explain how to do this loss of interactivity more smoothly.
Cool.
Okay. Very good. So paper 7. Juliet, there is this first question. Would you like to answer?
Yeah, so regarding the delay for the Raspberry Pi and why it's significantly bigger. So obviously, so our measurements for the delay includes client-side delay. So that would be receiving the video packets, decoding, rendering. So the main problem on the Raspberry Pi is the decoder implementation, actually. So for a number of reasons, it has to retain a couple of frames in its buffer before rendering it. So we need to know about null units, terminations, introduces. And so that introduces at least 3 or 4 frames of delay. And we can't do anything about that. It's the decoder implementation within FFmpeg. So it's not a lack of trying. So that already kind of adds on, I don't know, about 100 or so milliseconds of delay on top of that. Other reasons would be firmware of the Pi. So it's quite a simplistic single core device. So that means it can't process network stack in parallel to anything else. So if you compare it to the NUC, that has multiple hardware cores. And also the graphics card on this device is pretty ancient. It's from 2012, so that probably also delays the rendering as well. So it's basically lots of little things that add a frame or 2 here and there, and that adds to a number, quite a large number of delay. But I think in terms of 300 milliseconds delay on such a low-end user device, I think it's still a very good result.
Sarhan, does that answer your question? Let me mute you as well, just a second. Yeah.
Yes, thank you. So I saw that you also evaluated for MacBook, so MacBook, Android, and Raspberry Pi. So obviously you got the lowest latency with Intel NUC, and with that, does that mean that it's the most powerful device that you tested, or?
Yeah, I would say that it is the most powerful device. Obviously, the better quality processing, the quicker it will kind of go through that decode rendering loop. So MacBook Pro isn't far behind, but yeah.
Okay, thank you.
One additional question there. Do you have do you know where exactly this delay is forming? Is it in the network interface? Is it in the CPU? Is it in the GPU, or between the GPU and CPU, this data buses?
It will mostly be in the network. So the interesting thing actually is that we tested it on work Wi-Fi, which is quite congested. So I think that was quite a challenge. We challenged ourselves. But yeah, so we did some initial measurements. So there's the network delay. I'd say the decoding and rendering takes about a frame. The experience delay, so I know there was another question here of what the experience delay. That's the delay that it takes the experience itself to render. So we did some measurements of, if I'm on a local server, so we had a local server with a NVIDIA card playing that experience. If I moved my mouse, how long would it take until I would see the frame moving? So that's what we call the experience delay, and that was about 25 milliseconds as well. So there's some delay there as well. And the rendering, yeah. So depending on devices, we're counting in, I don't know, 10, 15 milliseconds for each kind of aspect of the decode line, essentially.
Okay, thank you.
Thank you.
So I'll go back to, well, we have, I guess, maybe room for one more question. I'll go back to the first paper, and the second question there can be perhaps handled. Kashyap, would you like to handle that?
Yeah, do you mean since the same event?
Yes, that one. That's the second question. Yes.
I mean, I think I have answered the second one. Maybe I will take up the first one because.
Okay, yeah, sorry, you're right.
Yeah.
The first one, yeah. It's a new question which came. Okay, yeah, go ahead.
Yeah. So with respect to navigation, if the viewpoints have overlapping timelines, then it will not be completely free transitions, because the user needs to provide some kind of an interaction. But however, if viewpoints have non-overlapping timelines, then it could be completely free. And yeah, the current demo supports such navigations where viewpoints do not have overlapping timelines.
Karsten, does it answer your question? Just a second, I will unmute you.
Yes, absolutely. Thank you very much.
Yeah, thank you.
All right, so I'm moving on to paper 3. We still can maybe take 1 or 2 more questions. So Jack, would you like to answer the second question then?
Yeah, that is definitely the plan, that we will reduce that latency. I've actually answered it in the Slido, so you can see a longer answer there.
Oh, sorry. Yeah, okay. All right.
Yeah, but the point is that we think that the low number for the small system, that is a number that is also reachable for the big system. We will just have to throw more processors at it. So the thing is, we think we can get pretty low.
Serhan, is that okay? It's answer for you?
Yeah, thank you.
All right, very good. So maybe one more question from paper 6. There are 2 questions. Let's take the second one. Emmanuel, would you like to answer that one?
Yes, so concerning the user studies, we plan mostly to focus on the user experience aspects. More specifically, as you noticed, we are using the wrap transition, which is, we consider it, if it's slow, to be smooth enough, and always starts from the back of the user in order not to disturb the experience. And so we will also like to see like different aspects, for example, for the lighting of the virtual scene, how it can be adjusted according to the content, etc., etc. And in order to achieve that, we plan to start a collaboration with a creative college here in the Netherlands, that they also have filmmakers that they are using 360 video, and they have some same concerns as we do, and do some joint studies together.
Thank you. Roberto, I guess you're still online. I'll unmute you. Is that okay as an answer for you?
Yeah, it's perfect.
Okay, very good.
Thank you.
All right, so maybe one last question so that we also finalize the second round. So although to Juliet, we asked another question in between. I asked another question, but can you then, Juliet, take the next one?
Yep, sure. So how is the storyline represented? So in terms of user story, if you mean what decides what is shown on screen when, so in terms of the demonstrator itself, as in navigating through content and then playing an experience or another, that uses a finite state machine. So user selecting content is a state, user watching video is a state, user controlling video is a state. And that's of course implemented in our C++ code. And then within each type of experience, so for example, I talked about the interactive branching narrative experience. Each type of experience is kind of a subsystem. So that particular type of experience actually is built on top of a data model. So we've got another team in R&D who are in charge of creating production tools to author and play back object-based narratives. So we've actually implemented a version of their general purpose player in our demonstrator. So if any story respects that data model, it will be able, that the player will be able to play it back. So it's a general purpose player. The player itself is implemented in our code base in C++, but the story is described by a data model.
Oh, wonderful. Thanks.
Okay. I guess we went 2 rounds. Actually, we started like 10:06, so we can go maybe even one more round to be exact, to give exactly 1 hour to the whole session. So I'll then go back to the beginning again. So Kashyap, would you like to take the next question here?
Yeah, maybe the last one.
Yeah.
Yeah. So currently OMAF supports only like images, text, and video and audio. So, and also maybe mesh. But in our demo, we have only implemented for images, text, and video and audio. We are yet to implement the meshes. And as far as interactivity is concerned, the one is switching between viewpoints, and the other is interaction with the overlays. For example, the overlay can be rotated, enabled, or disabled. With respect to 3D audio, so the current OMAF supports only 3DOF kind of interaction. So yeah, nothing beyond that. With respect to synchronization, so we use something called as extractor tracks from the ISO-based media file format, which helps us in synchronizing the background and the overlay. So we kind of frame pack both the background and overlay within the same video frame, which helps us in currently synchronizing both of them. However, if they are as a separate tracks and decoded separately, then the synchronization is done during the rendering. Yeah,
Okay.
thanks.
Thank you. Roberto, what's the answer for you?
No, yeah, it's perfect. Sorry for all the questions, but thanks.
Yeah, that's fine. Thank you.
No problem. All right, I'll move on. Then paper 3. I guess we can take the next question. Jack, would you like to? Is that the one from me? Yeah, I guess that's the one from me.
Yeah. So that is end to end.
Already replied. Yeah, please go on.
That is really the whole point of the exercise. So it's yes, we are definitely going to look at that next year.
Yeah, that's also one of the major topics in point cloud coding in the MPEG side as well. So that could be quite interesting to see your angle how we would look into this problem.
Yeah.
Right, thanks. So I'll move on. Yeah, I guess we finalize these. These are all 2 or under 3. So I'll go. Actually, we'll continue here, Jack. Next question is from Emmanuel. Yes. You received most of the questions, 6 questions. Very nice.
Have we extended the dash specification? Oh, no, sorry, I'm picking the wrong one. So
I think this one you should be. Yeah, I will open also your answer. Yeah.
Yes, so I've answered that already. So in practice, in the demo that I showed you at the moment, there is a single decompressor, but architecturally we have 1 decompressor per tile or per tile stream, and they will be resynchronized in the renderer. But so architecturally, the decoders are independent. Does that answer it?
I checked, but I guess Emmanuel currently is not in the session. But I guess you answered it. So let's then take the next one.
That's a very interesting question, Juliet. I am not quite sure whether we've had to extend the dash specification. We have done our MPD file is a perfectly normal MPD file. We have, and I always mix up the term fragments and segments, but so we are switching on fragment boundaries, but our minimum latency is dependent on the segment size, and that seems to be allowed. But look, if you look in the paper, you'll find a couple of references for where we got the ideas from. Maybe that's the best answer. Is please look in the paper. We think we are within the specs.
Does it answer your question, Juliet?
Yeah, it's interesting to see how we can manipulate MPD files and different types of experiences to fit within dash specification, as we're entering the realm of non-linear videos, etc. So we're looking at kind of how we fix these problems.
Go on, please, Jack.
Yeah. So the one thing that we need to cater for is that, you know, if you have a very fast receiver, you might overtake the sender, and then you you hit the end of your fragment, and you would sort of need to know, okay, so I hit the end, but this is not a permanent error condition. I should just retry, and then suddenly new data has appeared. So that's a bit of a trick that we need to do, and we need a bit of help from the Dash server for that to make it efficient. But it does all seem to work.
Very good. And I guess the next one is from Roberto. The last question.
About spatial audio, that's an interesting one. I had considered it a rendering issue. What we do at the moment, not in the demo that you were, actually, yeah, it is in the demo that you saw. So the demo in the audio in the demo is spatial. It is just that it is, you know, it is coming from where the point cloud is also based. So it's the spatialness of the audio is purely a function of the rendering. So that basically means that the Dash doesn't have to care about it. Does that answer the question?
Yeah. And for supporting spatial audio in Dash, you probably need some extension, right?
I would think so. I'm not, so the Dash wasn't my main part, but I think you would have to, yeah, you would need some mechanism to move the audio sources. So yes, I think that for that you would need an extension to Dash.
Thank you, Jack.
Okay. Thanks to all for the questions, and I'm very happy that we also had the time to go over all the questions, ask questions. So it's pretty nice. But anyway, if you want to look into the replies again, it's in Slido, and you can check it out again. And I guess it's 7:10, so exactly the time that we have to finish the session. So that was pretty good. And I want to thank all the presenters for their hard work and nice presentations. And also, I know it's not easy to explain demonstrations or demos through slides or remotely. So I wish we were all in Istanbul right now and seeing the demos live, but perhaps next time. So tomorrow for session 2, we will continue from where we left. And I want to wish all of you a nice rest of the day or night, depending on where you are. So I guess we can close the meeting now. Thank you. Bye-bye.